halogen compounds. Okay. See, it's a very unique thing of the property of the halogens. Halogens, they react within themselves also, which generally don't occur with any other elements. Halogens react within themselves to form compounds known as interhalogen compounds of the type X prime, because symbol of halogen is X now, so we'll write now here X prime. Okay, N. Where X is the larger halogen atom with lower, but not lower will not be correct, lesser electron negativity. With lesser electronegativity and N is equal to 1, 3, 5, and 7.
Done, sir.
Okay. So let us see what are those. So X prime. Okay, here N is equal to what? N is equal to 1. What are those compounds? ClF, so it's called chlorine fluoride. Bromine fluoride. BrCl, bromine chloride. ICl. IBr. Now X prime 3. So N is equal to 3. Cl F3. Br F3. Br Cl3. I Cl. XX prime 5. So these will be higher. I told you higher oxidation states are always being formed by what? By fluorine. So it will be I Br pentafluoride. Iodine pentafluoride. And N is equal to 5. And X prime 7. Only one compound is there. N is equal to 7. It is iodine heptafluoride.
Done, sir.
Okay. Can I rub it?
Yes, sir.
Okay. Now interhalogen compounds are covalent and are either gaseous or liquids. Why? Because you know covalent compounds have lower boiling point and melting point. Okay. The XX prime bonds are the interhalogen compounds are polar in nature. These are polar molecules. They have dipole moment. And is due to the polarity of XX prime bonds. Why they are polar? Because they have difference of electronegativity. Because of the differences in electronegativities of the combining different halogen atoms. That makes this compound more reactive. XX prime molecule are more reactive than the original halogen molecules. What are the original halogen molecules? X2 when they combine within themselves, or X prime. Why they are linked? See, X prime. They have same electronegativity. The bonds are 100% covalent, difficult to break. But here you find these bonds are polar because due to the difference of electronegativity. So they break easily and react fast. This is because X prime bonds are polar due to the difference in electronegativities of different halogen atoms and has low bond dissociation enthalpy. Thus, they are more reactive than original halogen molecules. But this question they will not ask like this. They will ask in other way. You write why is ICl more reactive than I2 or Cl2? Answer is same. So only thing is that what you write now here, you will simply remove this. You write ICl molecules are more reactive than original. Then what? Write down the answer again. Then I2 and Cl2 molecules. This is because ICl bonds are polar due to the difference in electronegativities of. We'll write now here large difference due to the large difference of electronegativities of iodine and chlorine atoms. plus I shell is more reactive than I2 and L2. A preparation you read from the book, only few, 2-3 equations are there.
Done, sir.
Okay. So now preparations you read, only 2-3 equations are there in your book. So now I'll go for the thing which is important is the structure. I'll draw it. Structures of interhalogen okay. So we'll follow VSEPR. Say it is X prime 3. I'm not doing X prime because X prime is linear molecule. 2 atoms are there, structure is always straight. See here. So this is the central atom. This. See now it has how many? Okay, put that. This is the central atom is X. This central atom. If you know the theory, you can write anything. Is X. So number of valence shell electrons. How many valence shell electrons the halogen has? Halogen has how many valence shell electron? Don't remain quiet. Tell right or wrong, you tell. Around 15, 16 students are there. None of you tell me anything. And when your result will be bad, parents is going to blame me. I think I'm going to have one Google Meet with your parents. Yes, in this month only I'll do. So tell me. How many valence electrons halogen has? What is
7.
the yes, it is
7, sir.
7. Good. It has 7 valence electrons. Now how many bond pair it has? See how many atoms has bonded with this? How many bond pairs? See how many atoms has bonded to X? How many?
3, sir.
3. That is In this covalent bond, you know bonds are being formed by sharing of electrons. Each bond contains 2 electrons. Out of that, 1 electron will belong to this, 1 electron will belong to this. Okay. So now here, in that case, how many bond pair it has? 3. Out of 7 electrons, 3 electrons of this X is being utilized for bonding. So how many electrons left? Out of 7 electrons,
4.
good girl. So 4 will make how many pairs?
2 pairs.
Huh?
2 pairs, sir.
Okay, then good. Lone pair is what? 2. All right. Then this is, what is the structure of this one? Structure is, what is the model? Model is A, B3, E2. So what will be the structure for this one? What is the original structure? I showed you in class 11. Original structure, you think that these are also B. So it is A, B, 5. This is the model. So see now. So this is for what? This is, what is the structure? I'm writing this one, not this one. This is the original one. This is our original model. See this. Do you know the name of the structure? Hello? What is the structure we call it?
So skeleton structure.
Yeah, what is the structure? It has a shape or not? What is the shape of this one? The shape of this one is pentagonal bipyramidal. See, these 3 and A is in the surface like this, and this is the axis. See, B is here, it is here, it is here. One B is on the top, another B is at the bottom. So its original structure is pentagonal bipyramidal. This is the original structure. But what did you find here? Actually, you find these 2 are missing. So if these 2 are missing, see, you can see an atom. Can you see an electron? Huh? Electrons are not visible. Original structure is pentagonal bipyramidal. But as these are not visible, what should be the structure of this one? What should you call it?
Sir, trigonal.
Baby, see here, I just turn it this side. I know you are having some problem of imagination. If I turn it this way, will it not look like this? I have turned it in this way. Will it not look like this? See here, is it not the same structure?
Yes, sir.
Then how does it look like? See, these 2 are not visible here. How it will look like?
T-shaped.
Correct. So let me now remove it. Okay. So it is, I'll write here now. It is AB3E2. Means what? How it will look like? See here, this is central atom. This is X prime. This is X prime. This is X prime. And these are the lone pairs. As it is not visible, so it is T-shaped. Okay. So whatever the molecule you have taken, see, we have given so many examples, remember? We have given there BrCl3. Then I've given you 3 examples. Not 3, 4 I have given. BrCl3, ICl3, then ClF3 and BrF3. No, all of them are going to have T-shaped structure. This is important for your exam, T-shaped. So this is our theory, this is our application. So you don't write individual wise, because if you have learned for this, then you may have confusion for this. So learn with the main molecular formula, and automatically all of them will going to follow the same rule, same structure. Done, finished.
Yes, done, sir.
Okay.
Sir, I have a question.
Jarur, bolo. I'm very happy.
Sir, in the book it is written bend T shape. Why is it so?
Correct. Because when the sizes are bigger, no dear, so there will be repulsion between this lone pair and bond pair. So it will come down little bit. So actual structure is, see, because of this repulsion now, we know lone pair bond pair repulsion is very high. So what will happen? What will happen now? X, X prime, and X. So this is because of they call it band T shape. See, do you sometimes come by local taxi to school? Do you go? Or you go to PB and all these places by local taxi? Sometimes do you go?
Yes, sir.
So generally, 3 of the persons are supposed to sit in the back side of the Maruti taxi. Sometimes they take 4 also, no?
Yes, sir.
Then in that case, can you sit properly in the seat?
No, sir.
Does it not happen? Some goes forward and some backward. Because of what? Because of repulsion. So same thing happens. Because of that, they told it bend T shape. Otherwise, if you write T shape, 100% correct. Okay. Now we'll go for X prime. I'll just teach you the theory. The rest you'll find. You will not, even if you try also, you'll not be able to forget. Then I'll go for X prime. Central atom is X. Now number of valence is 7. How many bond pairs you have now?
5, sir.
Very nice. That is 7 minus 5. How many lone pair you'll have?
1.
Very nice. 1. So I can write this one to be what? AB5 E1. See, in our original model, we have not taken into consideration the lone pair. We have taken lone pair later on. So it is equivalent to what? AB6. Do you remember the AB6 structure? How does it look like? See, when you take 2, it is linear. Means if it is A, B2 is linear. AB3 is trigonal planar. AB4 tetrahedral. AB5 pentagonal bipyramidal. And AB6 is what?
Hexagonal.
Cone octahedral. It is octahedral. Okay, so please don't think it is in the same plane. See, this is the one. See this one. So this is the one. See, it is. Here you have one, here you have one, here you have one, here you have one. So this A and 4B are in the plane. Here is the A. And see, this is the axis. One B is here, another B is here. So if you join from here and here, it looks like a octahedral. Okay, see, many a time that you buy this earring which is made of crystals, they have the octahedral geometry. All right, so this is the octahedral. Now see here. Now one is less. One here actually is AB6, but the actual molecule is what? AB5U1, that is in one place. B is not there. Electron is there. So when you see, will you see anything at the bottom? You will not see anything in the bottom. Only the upper portion you will see. So let me draw it now here. It will be X. X prime. X prime and X. So I'll draw it now. See here. So this is the axis. So how does it look like there? See, bottom is lone pair, you cannot see. So how does it look like?
Sir, pyramidal.
Yeah. There are two types of pyramids are there. Triangular pyramid and square pyramid. So what should you call it?
Square pyramidal.
Yes, square pyramidal, because the base is square. So this is called square pyramidal structure. So what is the original molecule we have now? Original molecule we have BRF5, IF5. Suppose if I write for IF5, so it will be like this. And this is with this. So if you wish, you can draw the lone pair, or if you don't draw the lone pair. You write here, square pyramid. So BR also will have the, sorry, this also will have the same thing.
Done, sir.
Okay, now I'll go for X7. I told you only one molecule is there. So in that case, I will not write XX7. I will directly write here IF7. Only one molecule. Okay, central atom is I. It has 7 electrons. And how many bond pair it has?
7 bond pairs.
Yes, that is, it does not have any lone pair. So it is bond pair 7. Here no lone pair. So what is this model? The model is AB7. This is not given in your book, right, in class 11 and in your class 2. But this is important. So I'll start from beginning. See here. AB2. So what do you write? A, B, B. AB3. Where do you put an extra B? We put it here. Moment I put extra B, see, if I put it here, it will be 90 degrees to each other, so there will be repulsion. So avoid repulsion, what will happen? See, it will be like Okay, like this is one dimensional, this is two dimensional. This is linear. Science is not difficult. What we will call it? The two dimensional. We call it trigonal planar because it is in same plane and it forms a triangle. Now I want to introduce the fourth one. Okay, fourth one, if I put it, then what I'll get it here? I can get it here. Don't write. Try to understand. Cone. Here bond angle is 120. Moment I put another one is 90 degree. So there will be repulsion or not? There will be crowding. So that due to crowding, there will be repulsion. So in that case, what happens? The atom comes from below or from above. So when it comes from below or above, what happens? See, now it becomes three-dimensional. It becomes three-dimensional. Now, what is the difference between square planar and this? In square planar, it was 90 degree. Here, the bond angle is 109 degree. So, there is a difference of 19 degree. So, the repulsion has decreased. So, what do you call it? Tetra. All right. Now, I am to put another one. AB5. What should I do? See, upper part one is there, lower part nothing is there. So, I put B from the below. When I put B from below, then that as this all the bonds were hanging down. When I put to above repulsion, they come up. When they come up, see here the picture. Picture is this. This is the original B. A, you have put this B from top. Then in that case, what happens? All of them they come up. See. Then what is this? This is called what?
Pentagonal.
Trigonal bipyramidal. See, this is in the plane. See, these three are on the top. So is it not? Is not the pyramid? I told you pyramid depends upon the base. See, 1, 2, 3, trigonal. If you put one, square pyramid. Okay. So there are two pyramids. See, one pyramid is on the top and another is the bottom. So this is the structure. Because of that, we call it trigonal bipyramid. All right. Now, when we go for AB6, what happened? I will not draw it here. Now, see, this top and the bottom position is blocked. So, where can I put? I'll put it here like this. Moment I put it here, what is the structure? See here, A. These are already blocked by B. So, here I put one more. Moment I put one, see, in this case, three were there in the same plane. Then what happens now? The fourth one comes. See, what is this? Octahedral. Octahedral. You can tell this one, see, here the base is square, you can call it square bipyramidal. If it is triangular bipyramidal, it should be square bipyramidal. But anyway, we did not use it because in geometry, this structure was already known earlier. So because of that, we did not put another new term. We don't call it square bipyramidal, but structure is square bipyramidal. And we call by its original name, octahedral. Now, why I have to tell you so much? Now it is one more is there. So I cannot put the seventh fluorine here and here. I have to put in the same plane. So here in this plane, you have 3 atoms. Here in the planes, you have 4 atoms. Then I'll put the 5th atom also in the same plane. Now, how it will look like? This is a lesson that you have learned from geometry, nothing to be scared of the chemistry. If you are being asked to make at home, you also would have made the same thing. I know by the theory, you know by your practical knowledge. So what I'll write now here, I'll put I like this, I'll put one F on the top, F at the bottom. So there on the plane linked to the ideal, there will be 5. So what I'll do, I'll put 3 in one side and 2 in another. Okay, so I'll link it like this, this. I'll write now here F. But only thing remember that this is the plane and this is the perpendicular. Okay, what is the name? We call it pentagonal. See, is it not pentagon? We call it pentagonal bipyramidal. So we have seen trigonal bipyramidal. We have seen square bipyramidal. But square bipyramidal, we call it by octahedral. And this is pentagonal bipyramidal. I have written only for your entrance. This is called pentagonal bipyramidal.
Done, sir.
Okay, just a minute. So now I'll go to group 18. I'll go to group 18. So group 18, what are the elements are there? Group 18. Elements, what are those? It is helium, neon, argon, krypton, xenon, and radon. This is radio. General electronic configuration. Is what? NS2, NP6. Exception is what? Exception, helium is 1s2. Okay. So after that, what do? We talk about these physical properties. So now we'll write here physical properties. Then what do you write after that? Atomic radius. See here, I did not write ionic radius because we know it has a very stable octet configuration. So because of that, noble gases or group 18 elements, we call them as inert gases or noble gases. Inert gases you understand because by the time inert itself you know that they do not react with each other. Then why do you call them as noble gases? Do you have any idea? Huh?
Because the last shell is full.
No, no. This one, whenever you say noble means something is very dignified. Here the noble word is being used, not in respect to them. Okay, it is a satire. See, the word noble initially associated with king's court. Those wise men who used to sit around the king and to counsel him, they were called noble. But interestingly, you know, those days noble people never used to mix up with the common people, thinking that they're something great. Because of that, they are being called noble cases. They don't interact with others. Okay, atomic radii. Please remember, noble gases that do not combine with others. Of course, I'll write some examples later on. So, whenever we measure the radius of an element, we try to find out the radius. We try to find out the radius when it combines with others. Because of that, atomic radii are called covalent radii. We allow the elements to react with other, find their bond length, and from there we subtract the radii of another element whose value I know. Because a covalent bond is nothing but the sum of the radii of both of them. If you know one of them, subtract from covalent radii, then you get the other. Okay? So, but noble gases do not combine with others. So, in that case, what should you call that atomic radii? We call them as van der Waals radii. Okay? So, we call van der Waals. Sorry. Van der Waals. They do not combine with others. Please remember, van der Waals radii are the largest in size. So when we had been discussing right from group 15, 16, 17, we have found that whenever you move from left to right, the atomic radii decreases due to increase in their effective nuclear charge. Please remember, in group 18, the elements which theoretically is supposed to have the smallest atomic radii, no. The group 18 elements have very large radius, and these are not covalent radii, these are all van der Waals radii. As they do not combine with others. Have you seen the cotton candy?
Yes, sir.
Cotton candy is very fluffy, na? If
Yes,
you
sir.
press it, what happens? Will it not come within your this palm?
Yes, sir. It becomes smaller.
Yes. So covalent radii is that it is a compressed radii. But in case of the noble gases, as they do not combine with others, so it is shape is very fluffy like the cotton candy, and that we call it van der Waals radii. So please remember, in periodic table, the smallest atomic radii belongs to group 17, not group 18. Group 18 has very large van der Waals radii. So we are not going to use the atomic radii, we will call it van der Waals radii. Clear? Understood? Okay.
Yes, sir.
Yes, sir.
Now you will read from your book. See, next is ionization enthalpy. Group 18 elements have very high ionization enthalpy. Why? Because they have very stable electronic configuration. So they do not try to lose electron. They don't form cations as such. So group 18 elements have very high ionization enthalpy. But if you go down the group, it decreases. It decreases because increase in their van der Waals. I will not write atomic radii due to increase in their van der Waals radii. Then electron gain enthalpy. Group 18 elements have either zero or positive electron gain enthalpy. That is, they never form an ions. They have either zero or positive electron gain enthalpy. Group 18 elements have zero electronegativity. Zero electronegativity. So now we can say why group 18 elements are chemically inert. If someone asks you that why they do not form compound or chemically inert, we'll simply write that group 18 elements have very stable octet configuration. Within bracket you write for helium doublet, and due to that they have very high ionization enthalpy, zero or positive electron gain enthalpy, and no electronegativity. So hence they do not react with each other. They do not react with anyone. All right. So now we'll go for melting point and boiling. See, group 18 elements all exist in gaseous state. But how about their melting point and boiling point increases down the group? Because you know, as the size increases, intermolecular forces of attraction increases. So they have very low boiling point. They are very low boiling point liquid, and they exist in the gaseous state. So this question may come: why the group 18 elements have very low boiling point? You will write the group 18 elements have very weak in van der Waals forces of attraction or intermolecular forces of attraction. Hence, they are low boiling liquids. Okay. Now, I told you that group 18 elements, they do not react with, they do not form compound, they are chemically inert. But we have found that among the group 18 elements, xenon and krypton, they are found to form some chemical compound, but they only combine with fluorine and oxygen. They do not combine with others. So they form some fluorine and oxygen compounds in the form of.
So why only oxygen and fluorine?
Yes, correct. Very nice. See here, when suppose you have some money in your pocket and you don't want to give. Any persons which persons come and told you that please give me some money, you tell no, I will not give. Okay, I'm not going to share my money with you. Or suppose if he has the same strength as you also, then also you can resist. But if a person comes who's stronger than you, can you stop him?
No, sir.
Can you stop him with taking the money from your pocket?
No, sir.
Yes. So which one is the most electronegative element in the entire periodic table? Which element is the strongest electronegative element?
Fluorine.
Fluorine. Then comes what? Then comes
Oxygen.
oxygen. Because of that, this fluorine and oxygen can forcefully take the electron from xenon. Why xenon? Why not from helium and neon? because helium neon the sizes are small. So the nucleus hold their valence shell electron very tightly. Xenon is a pretty large atom there. So in that case, the valence electrons are far away from the nucleus. So fluorine can forcefully take this electron from there. Okay. So xenon
Yes, sir.
forms compounds like XCF2, XCF4, XCF6. What oxygen can form XCO3. And they can also form mixed compounds like XCF2, XCF4, like this. But these compounds are not directly formed from xenon. We prepare this type of compound first. Okay. So here also in your textbook, you will find, I don't know, because if I give you, the load will be too high for you. So please read the preparation of this compound. Preparation will never ask for in any exam, but still just have a glance. So I'm going to discuss here the reactions of the xenon fluorides. Okay. So reaction of xenon fluoride compounds. Okay. First one that I'm going to react is called hydrolysis. See, hydrolysis is the most favorable reaction for any chemical compound. Hydrolysis means what? Reaction with water. This is extremely thermodynamically favorable reaction. So I'll classify it into two categories. Complete hydrolysis means all the fluorine will be removed here. Complete hydrolysis. Okay, so I'll write now here XCF6 plus 3H2O, it will give you XCO3. Just now I told you, no, this is the one. It's not direct prepared. We prepare this, from there we get this. Plus what we will get here? 6H. Now, if I have taken XCF4, xenon tetrafluoride, so it will give you 12H2O. All these reactions are taken from your book. Okay, so I did not write anything extra because you will have problem. 4XC plus 24HF and 3O2. But you don't worry, this is the only one which is important. Okay, 2XeF2 xenon difluoride. So it is 2H2O. So it will give you xenon 4HF plus O2.
Done, sir.
Now we'll go for partial hydrolysis. partial hydrolysis. So you will get now here Xc, that is all the fluoride, fluorine will not be removed. So it is H2O. You will get now here is called xenon oxidifluoride. 2HF. XCF6. H2O. You will get now here xenon oxotetrafluoride. And XCF6 2H2O is xenon dioxidifluoride. You get this. Okay.
Done, sir.
Answer.
Okay. Now the thing which is important for you of this one is the structure. So we'll write now structure of xenon compounds. Structure of xenon compounds. So here also we can follow BSCPR model. See, what is the outermost configuration of xenon? Octet. So how many valence electron it has? 8. Okay. So now I write here XeF4. So valence electron is what? Electron of xenon is what? 8. How many bond pairs? Now do you know? Bond pairs how many?
4.
Correct. Lone pairs, you know, 2. So what should be the model now here? AB4E2. Is it not equal to AB6? AB6 or not? So
Yes, sir.
if it is AB6, it should be octahedral. So what you are going to have? See here. I'll write here this, write here this, write here this, write here this. Here you put electron and here you put electron. See, it is supposed to be octahedral, but in the top and the bottom we have put lone pair. Why I did not put lone pair? Because it's 90 degree. Repulsion will break the molecule. So they are diagonally opposite. So this is also not visible. This is also not visible. So what should be the name of it? Square planar. Square.
Done, sir.
Okay. So now I'll go for XCO F4. All right. Now see. How many bond pair it has? How many atoms are here? 4 plus 1? 5, na? See, that is the biggest mistake of BSCPR, because xenon forms double bond with oxygen and single bond with fluorine, but they could not differentiate between double bond and single bond. Why? In those days, the concept of double bonds were not there. Okay. See now how to calculate lone pair. See, in this case, xenon has given 1 electron each to 4 fluorine. So 4 electron is being used for sigma bond. It has given, because oxy here, xenon is forming double bond. So for this double bond, xenon has given not one here and one here, 2 electrons. So total number of electron used for bonding by xenon is how many? How many? 4 for fluorine, 2 for oxygen. So 8 minus 6. 8 minus 6 is what? Sorry. Yes, 2. So it is only one lone pair. So what will be structure? See here, it is AB5. So in this case, what will be the, oh, sorry, the structure is this one. See. So what should I call it? I'll call it square pyramidal. It is square pyramid. This is important for your exam. All the general structures are important for your exam. So now I'll go for XCO3. I'll write down directly. See here. This is this. This is this. Out of 8 electrons, 6 are being used in bonding. And what is this? This is the lone pair. So it is called pyramidal. It is not tetrahedral, because tetrahedral, all the height should be same. Here nothing is there, it's missing. Height has decreased. So you call it pyramidal.
Done, sir.
Okay, now I'll not write anything, but I'll talk something to you. See, application or uses of noble gases is very important for your exam. Helium. Helium is used for making weather balloons. Helium is also being used for filling up the deep sea divers air tank that we have already discussed in solution chapter. Okay, so helium is also used for filling up or diluting the air in divers air tank. Next is what? Neon. Neon is used in filling up of electrical bulbs. They give a beautiful blue scintillations. So this neon is used for the advertising purposes. All these blue lights that you go and see in big cities for the advertisement, not deep blue, slightly bluish white. These are nothing but the filled with neon. After neon comes what? Argon. Argon is being used in maintaining inert atmosphere in chemical reactions. Argon is heavier than oxygen. It drives out oxygen from the air, which may oxidize the compound. Argon is being used in high temperature welding, because if you go for welding in presence of air at high temperature, the metal will react with oxygen and the metal will get spoiled. There will be corrosion. So in high temperature welding, we expel oxygen by supplying argon there. Okay. Then krypton is also used for making electrical bulbs. They are being used, they are being filled in the form of gas in electrical bulbs. All right. So xenon is being used in what? In chemical reactions. So all this, all the use of the noble gases, please read from your books. All right. Shumnath,